Okay, so let's continue with the cooling load from windows. A window, like a wall, has heat coming through due to the temperature difference outside to inside in the room, but also some heat from the sun. Some of the sunlight directly comes, some reflects or is absorbed, and some goes through the window to heat the room. And some is diffuse radiation from the sky and then into the window. Some bounces off or is absorbed, heating the window, and some goes through. Now, how much goes through depends on the shading coefficient. For a standard 3 millimeter thick clear glass, we say this is the standard with shading coefficient of 1. This much heat goes through. Now, for example, 2-pane double glazed glass with one heat absorbent or reflecting, both 8 millimeters, has a shading coefficient of half, 0.5. And the equation for the total heat has two parts. This part is just like a wall, the temperature difference, and this part is from the sunlight going through the window with the shading coefficient. So, the conduction of heat is very simple, the temperature difference. Now, for the window in this problem, we're using double glazed, 2 layers of glass, 3 millimeters each, one heat absorbent and one clear with no blinds. So the shading coefficient is 0.74 and the heat transfer coefficient is 3.49. If you have blinds, depends on the color, there will be a different shading coefficient. So we have the north window and the east window. The east window gets most of the sunlight because it's near sunrise, but some sunlight is diffuse and comes in through the north window. Now, how much sunlight is there? There's tabulated records of sunlight data through a standard glass window. We're doing 8 o'clock in the morning. So for the north-facing window, it's 38, and the east-facing is 591. So we'll use these for the solar load calculation. So let's do the north window. This is the heat load equation. That's the temperature difference, which we know from the outdoor temperature, and the conductance of the wall, the shading coefficient of the window, the amount of sunlight coming through, the area, one more time, and the total sunlight load through and heat load through the north window is 642 watts in 1 hour for that 1 hour. Now let's do the east window. It should be more. Same equations, same temperatures, same window. Shading coefficient is the same, but the sunlight amount is higher. Different area. Use the same equation, and we get a total from sunlight and temperature of 3,221 watts for that hour. Now let's do the cooling load from the inner walls. There's two inner walls. Now this one, we said before, this next room is also air conditioned at 26 degrees, so there's no heat going between these rooms. Same temperature, so no heat flow. But let's say this room is not air conditioned here. So it's somewhere between probably the temperature of this room and the outdoor temperature. Well, so let's say it's the average of the two. So this room will be 27.45 degrees. So it's just another wall problem with this equation. Temperature difference is 1.45. So for that hour, it's a 106 watt heat load. Next is the load from infiltration, any cracks in the walls or at the windows of some air coming in at some amount into the room. Now this room volume we calculated before, and for this problem we will say that the flow of infiltration air is equal to 10% of the total volume of the room per hour, or 1/10 of the air exchange. One air exchange is the volume of the room in 1 hour here. So we calculate and put it in meter cube per second, and that's the flow through cracks in the walls and windows here. There's two parts, the temperature difference and the humidity difference, the sensible and the latent loads. So the temperature difference, again we know the temperature difference for Tokyo in summer at 8 a.m. is 28.9 and 26. And the humidity difference from the absolute humidity, the absolute humidity is 18.1 grams, or 0.0181 kilograms per kilogram of dry air at 8 a.m. here. So those are the outdoor conditions and the indoor conditions, and we have to air condition this air into this air. So we know the flow from the problem. This is the equation. This is air density. Usually air density is 1.2 kilograms per cubic meter is good enough. And this is the specific heat of air, about 1 kilojoule per kilogram Kelvin, or 1005 joules per kilogram Kelvin. That's how much energy you need to heat the air or cool the air. Temperature difference in all these problems is 2.9. And the heat load from temperature difference, the sensible heat load, is only 24 watts. The latent heat load from the humidity difference is here, where R is the heat of evaporation or condensation for the water vapor. So moist air comes in, and we must dehumidify with this energy. The difference in humidity is here, from here to here. The total energy is 156 watts. Next is easier, the cooling load from lighting. So we have some lights in the room, and we said the heat load from the lighting per unit floor area is 20 watts per square meter with these lights. So easy, 1,638 watts. As you know, lights give off some waste heat and of course light. Now, the light will bounce around the room, hit a desk and bounce, or hit the walls and bounce around. But eventually, with all this bouncing, this light also becomes waste heat. Here, all the light eventually becomes heat. Now you know old style incandescent light bulbs make a lot of waste heat and some light. And more efficient fluorescent lights or LED lights make some waste heat and light. So for example, if this light bulb is 1,500 lumens and this fluorescent tube is also 1,500 lumens, sometimes maybe this would need a 100 watt bulb or a 20 watt fluorescent tube. So the waste heat would be different, but eventually it all becomes waste heat. So this light bulb efficiency with waste heat versus light is not important for this cooling load calculation, because all the light eventually becomes waste heat. We just take the wattage of the bulb or the fixture as it is, 100 watts or 20 watts or whatever. Next, cooling load from appliances, so computers, fans, coffee machines, kitchen equipment, boiling water, etc. For this problem, we said there were 30 watts per square meter of appliance heat for computers per unit floor area. So pretty simple. 2,458 watts. And we said for this office space, the latent heat was 0. So no steam or no moisture generating equipment. So probably in this room there's no coffee machine, and I'm not happy. Maybe the coffee machine is in the next room or in a kitchen somewhere else. Next is a load from the occupants, the people. People make heat, and people make moisture from sweat or breathing, and it depends on how many people. We said in this office space there are 0.2 people per square meter. So we know the area, so there's 16.4 people on average. Maybe sometimes 16, sometimes 17, sometimes more or less. And each person, sorry, that should be people, 53 watts per person. Makes 169 watts, that's okay. And the latent heat load is 64 watts per person of moisture, which needs dehumidifying for 1050 watts. So we've done most of the calculation now. Many different loads from the walls and the windows and the lights and the people for a subtotal of about 9,000 watts for sensible loads from hot things. And the latent heat loads from making water vapor, which we need to dehumidify, is about 1,200 watts. But we're not finished. We need some extra safety factors and things about fan heat and duct losses, and also the fresh air, the ventilation into the room. So, for a safety factor or accounting for heat from the fans and the ventilation system or loss from the ducts, for the room sensible heat load, we say it's maybe 5 to 15% of this. So for this problem, let's say it's 15%, a big safety factor. So the load we need is 10,427 watts. And then for the latent heat, we calculated this from all our loads in the room, and for a safety factor we'll do 5%, partly because the fan does not make latent heat, it's just hot, it doesn't make water vapor. So that's 1266. So with these extra safety factors, the room load and the air conditioning system, we need 11,693 watts. But we're not finished. Last, we need fresh air to come into the room to keep everybody healthy. So some fresh air from the outside comes in and then is exhausted out. Some of it is recycled as return air. But for us, we need to know how much energy do we need to cool this fresh air for the room. The problem says we need 25 meters cubed per person per hour, and we know there's 16.4 people, so the flow of air in meters cubed per second is here. So the sensible heat to change that air temperature from 28.9 to 26 is this equation with the density and the specific heat, so 398 watts. The latent heat to change this moist air to drier air for the room. Again, from the earlier calculation, we had delta X, the change in humidity. We know the flow, so we need 2,596 watts to dehumidify that fresh air. So for a total of almost 3,000 watts to condition that fresh air into the room. So we're almost done. The sensible loads we calculated from the lights and the walls and the people and the windows with the safety factor for about 10,400 watts, and the latent heat loads from people and from air in infiltration was about 1,260 watts with that safety factor for a total of about 11,600 watts. And then the flow of fresh air into the room, flow or fresh air for F, needed about 400 watts of sensible heat and about 2,600 watts of latent heat or about 3,000 watts. So the sensible heat load total, this plus this, is 10,825 watts. The latent heat load total, this plus this, is about 3,800 watts. And the final answer for the hour of 8 a.m. in this northeast room, the total air conditioning load is 14,687 watts. If you did this problem yourself, maybe your answer is a little bit different because of a rounding error or using slightly different numbers, but it should be about 14,600 or 700. Now, what does this mean? Maybe you noticed on some of the charts we used to calculate this TAC G, the TAC value. This is from the ASHRAE Technical Advisory Committee for the Climate Annual Percentile. We used 5%. So that means this is good enough for 95% of the days in the summer. On the hottest day ever, maybe this is not enough cooling for the room. But 95% of the time, this is good enough. We have to have some kind of standard. Sometimes you could use 1% or 2%, but we're using 5%, which is good enough. And we can use this to select the capacity of the air conditioner. Maybe round it up to 15,000, just to be safe. And that's it. Thanks for listening. If there are any things that were hard to follow, or my explanation was not clear, or maybe made a mistake, I saw one or two already in my PowerPoint here, please contact me, Greg Farnham at Osaka City University. And thanks for listening. Goseichou arigatou gozaimasu. And good luck on your final exam. Kimatsu shiken. お勉強に頑張ってください。よろしくお願いします。